Good morning, ladies, gentlemen, everybody. Welcome to the session called Back to the Future, a session organized by the NNV. My name is Johan Klootwijk, and together with Peter Brussaert, we are responsible for this session. Before we actually start, I would like to give the floor to our chair, the chair of the NNV, Diederik Jekel. Diederik.
Hi, Johan. How are you?
I'm fine, and how are you?
I'm fine, very
Okay,
well, very
great.
well. Looking forward to this session.
Please.
Yeah, so I would like to welcome everybody to this session on behalf of the Netherlands Physical Society. My name is Diederik Jekel, I'm the chair. And since 1921, 100 years this year, we've been the representation for all physicists in the Netherlands, whether you are a physicist working at a university or teaching or work at a company, we are here for you. And every year at Physics Veldhoven, we try to organize a focus session that is focused on something that is very important for physicists or interesting for physicists, but slightly besides the posters and the black holes and all kinds of really directly physics related stuff. And so we try to make the world a better place for physicists here in the Netherlands. And so we're always looking for new members. So if you're not yet one, please consider becoming one. And we are founded 100 years ago. And so we thought it would be interesting in our festive year to look forward for the next 100 years. So currently we're developing what's called Pad naar de Toekomst, a roadmap to the future. And the website of this Pad naar de Toekomst is live just right now. And if you go there, you can see something like this. And it's really interesting. It's sort of meant for all physicists and everybody who's interested to sort of together see if we can think how our future, what it will bring, what new inventions, what new ideas, what new discoveries will be made, and at what point in time will it be done. And so we maybe can think about something, how to organize this and how to make it happen, sort of have a roadmap. And with all the corona horrible things going on, we desperately need more functional roadmaps in our life. So that is why we have this amazing Pad naar de Toekomst, I think.
Thank you very much, Diederik. I think I take over now. Let me introduce the first speaker, because otherwise we consume too much time. And actually the first speaker is Professor Vincent Ikke. He's a professor of theoretical astrophysics at the University of Leiden. And besides that, he's a visual artist and a writer. He's our first speaker, and he will talk about connection, the past and the future. Vincent, the floor is yours.
Suppose that you want to have a theory of everything before the end of the century. What do we need for that? More experiments, more money, more people, more computers, artificial intelligence? Well, we will need all of that, except artificial intelligence, because even natural intelligence will not be enough. I will argue that what we need is something else. What we need is understanding. Wolfgang Pauli always asked for the key ingredient of a theory, was ist der Witz? And I think that the key to understanding is the hypothesis. Before I speak about good science, a few words about bad science. Nature has hardwired our brains to see connections. And the problem now is, when we see a pattern, does it really mean something? Or is it just a coincidence? Now, constellations are artificial intelligence in action, patterns without understanding. If purely a matter of chess, Go, Rubik's Cube, then artificial intelligence is superb. But for understanding, artificial intelligence is totally useless, maybe even dangerous or counterproductive, because a pattern is not a mechanism. If we want understanding, we must discover mechanisms. And patterns are just the beginning. Patterns may be deceptive, and very often patterns are deceptive. So we need something else, we need another ingredient. Now, some people think that discovery can be planned. They call it the scientific method, but actually this is not a scientific method, this is a political method. According to those apparatchiks, it works as follows. First you have a question, and then of course you must answer that question. That answer must be in a publication. The publication will lead to an application, because we need to make money, and that application then leads to the next question. Is this the scientific method? Absolutely not. This is not the way in which we proceed, and this certainly is not the way to the next century. This is counterproductive nonsense. We have known what we really need to do for almost 400 years. 400 years take us back to the middle of the 17th century. We start with an experiment, and that can be a natural phenomenon, or it can be something that you really construct in your laboratory. According to Christian Huygens, who wrote what you see in the background here, an experiment leads to an observation. And an observation is not just simply making note of something. Observation means you see something remarkable. You need to be attentive. Now, once you have observed something, remarked something, you need to formulate an idea about the cause of that observation. That idea you formulate in a hypothesis. And that hypothesis does not lead to an application. That hypothesis leads to something which is very much more important. It leads to a prediction, something that you have not seen yet, but something that you know must exist if your hypothesis is correct. And then you do a new experiment, and that experiment will determine, is it right or is it wrong, what you have predicted. And if your prediction is confirmed, then your theory based on your hypothesis can stay for a little, and otherwise it must disappear. Was ist der Witz? Das ist der Witz. What's the fun? What is the cue? What is the key? That is your hypothesis. Now, as I just mentioned, we have known this for just about 400 years, or a little bit less than that perhaps. So let me summarize what Huygens wrote about this. One will see here demonstrations, this is a quotation, one will see here demonstrations that do not offer as great a certainty as geometry, and may occasionally differ strongly from that, because where mathematicians prove their propositions by certain and incontestable principles, in this case, the case of physics therefore, in this case the principles are verified by reference to the conclusions drawn from them. The conditions of nature give us no alternative. Huygens says no alternative. Does that mean that facts do not exist? Oh yes, facts exist. But there is always room for improvement. How does that work? Still, it is possible to attain a degree of probability that quite often is hardly less than complete certainty, namely, when the things that one has deduced from the supposed principles correspond perfectly to the phenomena that observations show us, especially when there are a large number of these, and still more powerfully, when one formulates and predicts new phenomena that must result from the stated hypotheses, which then actually are found as foreseen. This is Huygens' summary of that cycle that I have given just a moment ago. He wrote this up in the preface to perhaps one of the most brilliant physics books that has ever been published, in the preface to Traité de la Lumière, a treatise on light. Was ist der Witz? What's the fun? The supposed principles, a supposition, not something that necessarily follows like mathematics, with your sort of definition, axiom, theorem. That is not what happens. You must suppose something. This was again summarized by this particular quotation. For now, for the first time, an entire natural philosophy is treated by Huygens as a hypothesis, the utility of which is not assumed to begin with, but must be tried and tested anew every time. By now, we are hardly aware that it was ever different. But before the years 1652, 1656, even the possibility of such an approach was not considered. These are the words by Professor Floris Cohen in his book, The Herschepping van de Wereld. My translation. Professor Cohen is a historian of science who sort of summarized in his way what Huygens has written in 1652. The key is the hypothesis. Process I've just shown produces the advancement of understanding, and the crucial element of this cycle is the hypothesis. Let me give a simple example. Clouds and rain go together. I mean, even my dog knows that, and nature does this experiment for us, and we can observe it. Rain, we observe, is made of drops. Rain and clouds go together. Now we notice something. There's an observation doesn't really mean that you see something happening, but observation is something special. Be attentive to something that is special about this. Rain and clouds go together. Now, if rain and clouds go together, maybe a cloud is made of drops. We don't live in the cloud, we just get the rain on top of us. Maybe a cloud is made of drops. That is a hypothesis. A hypothesis that says maybe if we see something happening, there is something behind it. There is a mechanism. There is something that is behind the clouds, as it were. Now, of course, you would immediately use your sense of logic and say it could not possibly be correct that a cloud is made of drops. Because if a cloud is made of drops, drops fall. We're talking about the rain. Why do not clouds fall like the rain? Aha, you think. Your hypothesis is refined, and you say, well, a cloud can still be made of drops, provided that the drops are very small. And if the drops are very small, they're carried by the streams of the air, and the big drops, the rain, fall down, and the small drops in the cloud just simply make these cauliflower shapes that you see so beautifully in the sky. Well then, raindrops make rainbows. We need to make a prediction on the basis of the hypothesis that clouds are made of droplets. Now, if clouds are made of small drops, our hypothesis predicts that clouds should also make rainbows. And what we observe is that this is true. Clouds do make rainbows, and our prediction is confirmed, and therefore our theory can go through another cycle. This cycle produces the advancement of understanding. The crucial element of this cycle is the hypothesis, and this is much more than just intelligence. You need more than intelligence. And what precisely do you need? Well, the interplay between cause and effect shows us what happens. And that, if you see what happens, is a matter of observation. Now, the next thing is that given a cause, there is something that can happen. I see a cloud, and sometimes it rains and sometimes it doesn't rain. So we have a cause. What can happen is the next thing. Now, to connect these and to see what could happen under various circumstances is what you might call intelligence. So you have a cause, what could possibly happen, you might understand. And now, given an effect, rain, we want to know how it happens. The effect is the rain. We want to know how does it happen. You need a hypothesis. The hypothesis that clouds are made of droplets. And if you put all of that together, you get understanding. Your understanding is something that is much deeper than intelligence, because that understanding is based on something that is not produced by an experiment, is not produced by nature, except, of course, that your brain is also part of nature. The part of nature in your brain hypothesizes something. It thinks, might it not be the case that? That is what leads to understanding. And if your hypothesis turns out to be correct, we understand what is going on. A hypothesis is a creation. A hypothesis is like a poem, like a painting, like a work of art. And therefore, to do physics, you've got to have taste. There is no method, there is no systematic cycle of discovery. Physics does not really discover immutable laws. Physics is more like biological evolution, and therefore be prepared to fail. Let me give you one more classical example that goes a little bit further than rain clouds. Max Planck had invented a relationship between the energy of light quanta and a time scale. And Louis de Broglie considered that there is another key item in mechanics, and that key item is momentum. Now, if there is a relationship between energy and a time scale, then dimensional analysis suggests that the relationship between the momentum of particles must be a relationship with a length scale. So the energy corresponds to a frequency in time, and the momentum corresponds to a frequency in space. That is the hypothesis, das ist der Witz, that's the idea. Well, Professor de Broglie, in this particular case, had a bad hair day, but he had a very good physics day. Well, about the future. We're trying to think 100 years ahead. 100 years ahead where we are standing now. And therefore, we have to ask ourselves, what is the experiment? What is staring us in the face that requires an explanation? Well, in my opinion, the most urgent item is the fact that 95% of our universe is not baryonic matter, the stuff that we are made of, the stuff that you see in the world around you. 95% of our universe is something else. And what is it? This cosmic dark stuff is not made of the particles that de Broglie considered that I mentioned just a moment ago. Nobody knows what it is. Even calling it dark matter, is what you so often see, is wrong. You can't call it dark matter because we don't even know that it is made of particles. Astronomers can see indirectly this dark stuff by means of the so-called gravitational lens effect. And effectively, that is all we know. We see, when we look in the sky, that the images in the universe, a very, very deep universe, those images are distorted by the presence of that dark stuff. That dark stuff curves space. The curvature of space imposes itself on the way in which light propagates through the universe, and in this way we can indirectly see by this gravitational lens effect that this dark stuff must be there. Finding out what this is requires all hands on deck. The observations are steadily improving, and now what we need is a good hypothesis. Understanding is much more than intelligence. If you want to know what the cause of an observed effect is, you have to create a hypothesis. Physics goes back to thousands of years before Huygens. It starts with an experiment sitting down in the afternoon and looking towards the west. That is step one. During this experiment, we see the sun going down, and that is step two. And now comes step three, the crucial step, the hypothesis. Earth is a spinning sphere, and the sunset is an illusion. Earth is a spinning sphere. Step four, the hypothesis, should give us a whole range of predictions that follow from this hypothesis, and every new experiment confirms this hypothesis. We understand the motion of the heavens. We see the sunset with our eyes looking outward. We see a hypothesis with the eyes in our head, our eyes looking inward. A hypothesis is a creation, but a hypothesis usually turns out to be wrong. Anyone who says that Earth is a spinning sphere must be joking, because you can clearly see that the sun is going down. Wolfgang Pauli always asked, was ist der Witz? Witz is a German word for joke. Fools make jokes. Yes, they call that person on the hill a fool, but I would rather be called a fool than a coward. So, what must we do? What steps will lead us towards the future? The task ahead of us is the same as it always has been. And this task was brilliantly formulated as follows. Our task is not to see what nobody has seen yet, but to think what nobody has ever thought about things that everyone sees. These are the words of Arthur Schopenhauer in a letter to Charles Darwin. Thank you very much.
Thank you very much, Vincent, for this beautiful talk. For the audience, I have an iPad here in my hand and I'm directly connected to my colleague Peter, who is in the back of the room. Via the chat, you can ask questions. And if you allow me, I have just one question that I would like to ask you, Vincent. Can conceptualization be learned or trained? And if yes, how? Only at the university. Could you please elaborate shortly on that?
Historical examples, like the one about quanta that I've just given, are always very useful. Read your history. Mm-hmm. Okay, yeah. Not just history of science, of course, but just read history. The second thing is that great teachers can help you. Just recently, one of my great teachers, Professor Martinez Feldman, passed away, and I can absolutely guarantee you that what you can learn from something like Tini Feldman in this respect is priceless. This is the kind of way in which you can try to proceed.
Thank you very much, Vincent. I would love to talk further with you, but we have given the time. I have to announce the next speaker, so thank you again.
Okay.
This brings me to the next speaker of this session, which is Dr. Charlotte Kjellander. She's working at TNO Holst, where she is a team leader in a wearable electronics group that develops the future concepts of conformal electronics for health. She will give a talk entitled How Smart is Electronics? Reflection from a Wearable Electronics Perspective. Charlotte, please, the floor is yours.
How smart is electronics? Electronics is around us everywhere. You hear about it daily, and today you will hear me talking about a couple of things, and it will ring a bell for you. I want you to see the electronics reflections from a wearables perspective. I will paint pictures in front of your eyes, and I want you to sense and feel the meaning of electronics that it had in our lives before and today in our daily lives. Think of it. How smart is electronics for you? And share your reflections in the chat. But first, let's connect. Be on the same wavelength. What is electronics? It's a physics about everything that has involving electrons and electronic devices. I thought I'd bring a lot of demonstrators, so I brought a set of 10 to the power 28 electrons with me here today. And I'm happy to see that on the other side of the screens, you did the same. Great. So that is electrons everywhere in our whole daily life, in ourselves and also in devices. So looking back to the last century, electronics played a major role. The computer is made. Already 2,500 years ago, 2,500 years ago, the first computer was made, the abacus calculator. But only the last century, these inventions really took space and got evolved further to computer, electronic television, internet, smart devices. And that's thanks to many physics inventions, transistor being one of them. And today we are flooded of devices. There's so many, and they impacted our way of living in many different ways. And of course, also our way of communication, where before we communicated making smoke signals, waiting, having patience, waiting to the answers coming, evolving more and more with the electronics developments to smartphones, to internet, where we have a communication and overflow of messages, photos, videos all the time. But has electronics actually made us think faster and respond quicker? Is electronics intelligent? Well, let's see what you think about this. How smart is electronics for you? Well, for me, actually, it's not smart at all. It's just a tool. So an example, the GPS. I'm happy I have one, otherwise I would never have found the studio here today. But does that mean that the electronics is smart? No, the GPS has a lot of knowledge. It brings me knowledge, know which road I should take. It also tells me when I should turn, when I arrive to the destination, when I should have turned, also tells me. So is electronics smart here? No, knowledge. Am I smart having the GPS? Maybe. Does that make me smart or intelligent? So the true sign of intelligence is not knowledge, but imagination. A quote from Albert Einstein. So think then, how can we imagine our future? That's a pretty big area, so I will not take the whole future. I will narrow it down a little bit to how can we imagine our future of smart wearables. All right, so what is wearables? Well, already the first wearable that were ever made, the abacus ring, maybe you remember from earlier, I showed the abacus calculator. In 1644, this calculator was made small, miniaturized to fit a ring for a salesman, so that he could make good calculations, good predictions of the sales and the tradings at the markets. The first wearable, it was small, it was functional, you could wear it close to your body. The true meaning of a wearable. Today we have wearables everywhere, and a lot of them around us. You know yourself, your smartphone, headset, Google glasses, a lot of gadgets, heated soles for in the winter to keep you warm, nice. But they're also coming up pretty useful wearables. For example, for the medical market, where you have smart plasters measuring the patient's physical status. But what if wearables can do more than just be cool gadget and helpful? Just imagine, what if we could prevent diseases with a solution that works intuitively? But this is easier said than done, actually. So why is it so hard to do this? Well, diseases is something very in the now. It's very concrete. You're sick or you're not sick. That's easy for us to understand. You're sick and you treat it and you get well. Naturally, we are drawn to these things that are easy to understand. And it makes it more difficult for us to understand what's happening in the future. So how can we actually prevent things coming up? We want to work on the short term. We also know that stress is a big problem today. We feel a lot of stress, it's heavy workload, we have a pandemic that's taking off the normal way of being and functioning. And also today we feel more and more lonely in this digital era. We have to be more involved. People have to be more involved in the process of prevention. We need to want to change our way of living and be active in that. imagine how we can make use of electronics for this, to solve ourselves in a natural way. Imagine how we can use smart communication and monitoring. Smart communication where we actually have the communication where we need it and for the meanings that are needed at that moment. Smart monitoring, really looking into the body, seeing what we have when we need that information. So one trend that I've seen coming up in this field is Moore's law, but in the wearables language. A bit different, still the same. Going from rigid, singular to invisible, skin-like. Having some samples here. Let's start with the calculator again, abacus. Useful, doing its work, doing its task. Having one singular task, doing the calculations, is rigid, still functional. Next step is making, or a step counter, same thing, doing its tasks, making the steps counted, still singular, bulky. Multifunctional, now it becomes more complicated. For example, the Apple Watch, not only showing the time, well, I don't think many people of the Apple Watch have it for the time, but it also measures your ECG and really your status of your body. And you can also use it for calling and reading your emails. Multifunctional. Still pretty bulky. The next trend is coming in to be more softer, conformable. Something that's close to your skin, something that moves, that's stretchy, that you can measure more signs on, as a lady there having on herself, or as this one, having a lot of functions measuring your vital signs on the body directly, non-invasive. Stepping further, we make it even thinner, skin-like electronics, tattoo electronics on the skin itself. You don't see it, you just have the function there. It follows your skin totally. And invisible, making it so small you can put it under the skin, or you can actually swallow it and it's inside your body, making the functions and seeing what you have inside. So, as you might see, you've seen these things before. Technology is there. Well, this small little chip on the finger, it's a public transport ticket that you have it with you all the time. It's been there for 10 years. Tattoo electronics was shown in academia 2 decades ago. So why don't we see all these products out of the market? It's because it's complex. It's a complex situation. There are many factors that has to interplay to make this work together. And it's important to see it's a human that's in the center, human-centric, where we have technology and design that makes fantastic products, but they have to have a meaning for the person, for its physiology. Ethics, privacy, sustainability should guide us how to protect the user, ourselves, now and the future generations. And, as we heard in former talk as well, business, someone has to pay for it, someone has to come up with a market on it. But everything goes around yourself, human-centric. That's wearable electronics, wearables. Another trend towards really human-centric electronics is force phase system, protective, interactive, communicative, intuitive. So to sketch this with some prototypes as well, look into the protective part, face mask. It protects a person against a gas attack. It's a pretty old one here, but there are other protective wearables, rather new ones. This one, for example, a cooling vest, keeping health workers cool during their excessive work in the pandemics actually right now, so that they are fresh in mind. Next step, the interactive. For example, another face mask, it's not only protecting the wearer, but it's also communicating with the wearer a bit, interacting with the wearer, telling, well, this face mask, you have to change the filter. We are sensing that it's not that accurate right now. Or, for example, another interactive one, as this first clothing piece. A shirt, interacting with the user, with the wearer, measuring the heart rate of it. To interact and tell the person, you're doing well now, or maybe you have to speed up a little bit to get on going further. But we can interact in so many other ways. We don't need to interact with our own body. We can also interact with the environment. For example, with the sun, as a solar shirt. At the same time, you're wearing the shirt, it interacts with the sun to take up energy and to store it in your battery, charge your mobile phone. So it's very technical, it's nice, but it also makes people aware, I have to go out more. I have to go out and be in the sun. So it's having a social responsibility as well. I go out, I go moving around a lot more, so you're actually getting in better shape and better condition. So the next step is a communication. As another example, we take one at a time. Another example here is the Body Wonders. The Body Wonders is a shirt that can give you an interactive hug. It can hug you on distance, or you can hug someone on distance. So it communicates with the user, or communicates with someone that's not even here. Making use of electronics inside, with vibration motors, giving the haptic sense of touch to the one who's wearing it. And the next step is getting this even further, having an intuitive way of communication. It's first having that the shirt that you see here, first interacting with the wearer, measuring the stress level, for example. And if you're stressed, it starts to help you decrease your breathing. Decrease your breathing in a regulated way to slow down your body functions so that you naturally prevent any damage to yourself. And in this way, being able to naturally and spontaneously continue with your life. So these are a couple of trends we see in human-centered electronics. And if you see also around in the world, we see that with the global pandemics, for example, it's important to take care of ourselves. Healthcare sector, we are getting more and more elderly people. We need help to take care of this, to have wearables helping us to understand our bodies. And we have also the Japanese initiative, Society 5.0, putting the human in center for everything. And that brings us also to the last point here. The future of electronics goes towards non-invasive, invisible, intuitive. Electronics that strengthen our expressive and communicative skills. Electronics that will support our well-being and increase our awareness. That is, for me, the smartness of electronics. Thank you.
Thank you very much, Charlotte, for your very encouraging story. Beautiful story. I have a number of questions. We have a little bit of time, but well, I actually like this question the most. These shirts, they are so cool. Where can we actually buy them?
They're really cool shirts. I must say that, indeed. We are developing concepts.
Okay.
So we are developing concepts, so we are not making products.
Okay.
But contact me and we can find a solution to developing concepts together.
I will post the answer to the question. Thank you very much. And the second question, we have some time left. So could you please elaborate on the integration of wearables and augmented reality?
Yeah. Wearables and augmented reality, indeed. So putting in wearables measure senses and can get feedback. Augmented reality can help in that way, so that you tell what kind of feedback you want where. on your body, in your clothing, to help you also your visual senses. It's happening already right now. I've seen at CES a couple of years ago. It's already coming more and more into the scene here. And that's a step forward, not only for gadgets, but also in operation settings where the surgeons are using it.
And then maybe a short last question. How about wearable for pets?
It's a booming business.
It is?
It is a booming
Okay.
business. Also at CES, especially this year, it's coming out a lot of pet tools measuring how happy your dog is, for example, so you can follow that.
Okay.
Horses is another big aim for that question. Race horses to measure the physical state of them following. Police horses and all that. So pet electronics is a booming business. Yeah.
Fantastic. Given the time slot, thank you very much again for your beautiful talk, and then we will go to the next speaker. Thank you. Our next speaker is Dr. Michiel de Lange. He's an assistant professor in New Media Studies, Department of Media and Culture Studies at the University of Utrecht. And amongst others, he's a co-founder of the mobility mobile city, www.themobilecity.nl. Mind, this is a talk that has been recorded before, so there will first be a movie that will be shown. But later on, Michiel will be online, so we can still have live Q&A via the chat, and I will get the answers again on the question on this pad. So there's time to have some chat with Michiel. First, I'd like to give the floor to Michiel.
Hello everybody, my name is Michiel de Lange. I'm an assistant professor at Utrecht University at the Media and Culture Studies department, and I want to take you on a short trip through the future of our city, which is slated to be a smart city. And I'm wondering, and I hope to discuss with you the question, how clever are smart cities really? So first, what are smart cities? Type in the word smart city in your favorite search engines, image search. In this case, I did Google. I prefer DuckDuckGo by now. And then you get a wide variety of images, most of them suggesting some kind of futuristic, forward-looking portrayal of urban life. Lots of glitzy images. I see quite a lot of models as well, which suggest that the complexity of city life can be captured in models. And I particularly find interesting also these two images with a hand in it. So the bottom right and somewhere just below the middle, there are hands holding cities. So this suggests that the city can be remote controlled like your television set, just by pressing a button. So it's all about cities that are infused with technologies, being able to control them efficiently. And that indeed is what smart cities are about. So they're about optimizing a variety of urban services in, for example, healthcare, mobility, governance, and so on, mostly using real-time data. And there's a whole variety of apps and algorithms and room-sized control rooms, interfaces, dashboards, analytics, services, and so on that are being developed in order to make these cities more efficient and to optimize these urban services. For example, here, South Korea, room-sized control room for remote controlling the smart city through interfaces and through all kinds of metrics and KPIs, key performance indicators. Maps, of course, are a crucial interface. Real-time images from CCTV cameras. Rio has a bigger one built by IBM, the Center of Operations, the Operations Center in Rio de Janeiro, which is probably the most famous control room for the smart city. So this is what the smart city looks like backstage, so to say. And according to some experts, we see 3 generations of smart cities. The first one being a smart city that is mostly technology driven. So here it is mostly these corporate products that are at the forefront and that define what the smart city is about. So all kinds of your Cisco, your IBM, your Microsoft, and so on, who are selling these smart technologies for cities. Then the second generation is more, municipal-led, more technology enabled, but driven by all kinds of interests by municipalities themselves. So they are at the wheel rather than the technology companies. So it's mostly public bodies, public organizations that all of a sudden now all want to become a smart city, because after all, who wants to remain a dumb city, right? So all want to be a smart city, so now they're competing and vying for becoming the smartest city. And the third generation of smart cities that we see is, or that is mostly being proposed, I would argue, is a citizen-led, or at least co-led smart city in which citizens are partially at the wheel themselves too. So whereas it's corporates in the first generation, public institutions, second generation, it's the people, whoever those people might be, who are at the wheel in the third generation of the smart city. But I think, and that's one of the points for discussion, we're not there yet. So what could a citizen-led smart city of the future really look like? That might be something to discuss later on. Summing up, smart cities, where technologies and cities and people meet. But it's not self-evident, because I think there's a couple of thorny questions that we should raise when it comes to smart urbanism. And I always like to split those questions into three sections about smart technologies. So how can we use technologies in responsible ways that actually generate value for us and for society, rather than just for corporates or platforms only. Second is about smart cities, about the cityness of cities. So what type of city do we actually want? How do we envision our future city? Do we really want our cities of tomorrow to look like these highly technological, controlled environments, or are there perhaps alternative visions? And thirdly, naturally flowing from the other ones, I would say, so they're all interrelated, what about the people? Who is actually supposed to be smart? Who benefits, obviously, and who have the right to decide about the future of the smart city? These types of questions I will briefly run you through before we get to the discussion of today. So first, the technologies. I think it's a huge challenge to develop and design technologies that can be used responsibly, that are actually beneficial to society and individuals. I just picked a few examples from recent years, how, for example, artificial intelligence being deployed in self-driving cars, which are predicted to populate the city streets in a near future. How there's various very kind of insidious algorithms that tend to recognize lighter colored faces, but not darker colored faces. So there's arguments that there's kind of this inherent bias that leads to an inherent racism in self-driving cars, which could lead to people of color being very unsafe in our city streets of tomorrow, which obviously is a very undesirable development when it comes to smart technologies. Or what about the real estate sector that is now, looking where can we divest our money, where can we, create new gentrification processes using data and algorithms. So these technologies lead to certain developments in neighborhoods that might not always be desirable, because as we know, while processes of gentrification on the one hand are an inevitable part of city life, they also tend to push out all their inhabitants and tenants and lead to all kinds of social upheaval and exclusion. So that's a thing to consider as well. Or what about the variety of cities who've experimented with predictive policing software, which appears to be super flawed in terms of its algorithms. So there's a promise to be made that neighborhoods can be made more safe with these predictive policing software, but in fact it only serves to affirm that certain neighborhoods are worse neighborhoods than others, and it tends to become a self-fulfilling prophecy. Not a responsible use of technology, I would say. Then there's the second point about cityness. How do we make sure that smart city developments actually produce future cities that are favorable to live in? Is this the type of city that we want to live in? Do we want to live in a city like Barcelona that is, well, I guess not now, but at least prior to the corona outbreak, suffering from massive Airbnb tourism that really leads to major, upheaval in the city and local residents feeling that they're being pushed out of their own city? Or Airbnb acting as a racial gentrification tool, leading to further exacerbating social differences between different groups? Or what about surveillance issues? Smart technologies recognizing us through smart cameras and facial recognition software, so all kinds of surveillance, personalized advertisements, knowing how and what you prefer to look at. So is that the type of city that we want, infused with various smart technologies? Don't think so, and I guess I'm assuming you don't either, but what then? Let's discuss this later on. Finally, what about smart people? We do know that the design of cities, the architecture of cities, or even the furniture in cities defines what good citizenship is about, so how we are supposed to act. So it's basically superimposing or prescribing, scripting socially desirable behavior, or perhaps not socially desirable, but only a very limited set of behaviors that, thou shalt not loiter, thou shalt not fall asleep with a beer on a public bench, or do not jaywalk, right? So all of these architectural elements prohibit citizens from lingering, loitering, doing something out of the ordinary. So they prescribe normal behavior, and that can, in fact, be very restrictive. Now, let's look at the smart city equivalent of this prescriptive design. And then I think we can see, and maybe you understand what I mean when I'm saying that it's also not just designing for the smart citizen of the future, but it's also designing that very citizen itself, herself or himself. So, facial recognition, superimpose this self-disciplining behavior upon people to not act out of the ordinary. Don't shout, don't scream. Microphones will pick up loud noises, may dispatch a police force to a certain location, see what's going on. So act normally. And who gets to decide what normal is? Or what about, smooth and frictionless finding of shops nearby? So the whole city turns into an optimal, streamlined shopping experience. And what about civicness? What about accidental encounters, bumping into somebody or places you didn't know and didn't even know you liked? So serendipity or friction. And what about all of the things that are typical for life in cities, namely dealing with strangers, dealing with people who are different from you? That has all been smoothed out, and this frictionless experience is created. Just like with the self-driving pod on the lower right side. Everyone in their own capsule, not meeting one another. No sweaty, smelly bodies rubbing against one another. No, it's a sanitized city, optimized for individual efficiency, but not for real civicness, which is about meeting and interacting and dealing with differences. So, to wrap up, I have two discussion points. First, my argument is that many smart apps tend to have, as an underlying logic, a really conservative politics. Think about the smart parking app, for example. Everyone hates to search for a parking spot in the car or in the city. So what about this smart app that can direct you to the nearest vacant spot? Everyone wins, right? Even the climate wins because there's less traffic in cities. Yeah, but, it tends to further optimize an already existing mobility paradigm at the expense of a more thorny, a more difficult political discussion about what type of mobility system or systems do we actually feel are desirable for our cities. So that's the first one. And the second one is smart cities really are the product of a very poor imagination. And we really, and that is my second argument, we really need the arts and creative thinking to imagine possible alternative futures for the smart city that are not technology-centered but people-centered, using playful experience, using artistic experience, also using data to engage people with their city. So think of alternatives for the future. That's it for now, and I hope to have an interesting discussion. Talk to you later.
Well, good morning, Michiel. Thank you very much for your interesting talk, and I'm happy to have you live over here now. I hope you can hear me.
Yes.
We have some time for a few questions, and I would like to start with the first one. Actually, you mentioned already in your talk, how about smart people? Well, automotive is prone to be easily hackable. How about hacking the smart city? Could you elaborate on that?
Yeah, I mean, there's actually two ways of understanding hacking. There's one understanding that is about the criminal activity of breaking in, unauthorized.
Yeah.
And there, I think there's a very real risk of breaking into various digital systems that are deployed to run and automate urban services. So this is a concern of security and safety, right? It's IT security. Very real. There's actually even a video game about this very topic, about breaking into a smart city.
Yeah.
So there's already all kinds of imaginative ways of playing with that idea of hacking into the smart city. Now, there's also a second understanding of hacking that is actually the original word hacking, which originates in software and hardware hacking in the US, basically just engineers interested in cracking open the black box, so to say. And here I think there's actually a more provocative and more interesting way of understanding hacking as allowing people themselves to sort of insert themselves into the system and deciding, at least partially, and also owning parts of the system.
Yeah.
Just like a software engineer would also, for example, create their own free software. And here I think there's huge potential for civic engagement in the smart city. So I don't want to dismiss hacking as just a danger. I'm personally very interested in the imaginative idea of hacking in the second sense.
Okay. Well, maybe related to that, you say already people may be owning parts of the data. How about the privacy in the end? Who actually gets access to all the data? How is that arranged?
It's a great question, and that is also often a huge question mark. Who actually become the owners of the data that citizens in the smart city generate? For example, if you install one of the free apps, then by now we know that if the product is free, you are the product. So you generate value by submitting data to probably a variety of businesses.
Yeah, most likely, yeah.
Yeah, and who knows what happens with those data? I mean, so there's a lot of discussion going on now about data ownership. Who own the data? Who get to decide and who get to govern and manage the data sets? Mm-hmm. And I think this is a discussion that we really need to have, and we need more institutional governance frameworks to manage that. Up to now, it's mostly almost like sort of a Wild West situation in smart city land. We need far better government regulation of data sets in order to ensure that our privacy is safeguarded.
Okay. Yeah, please. Okay. Maybe a little bit related to this, but also a little bit out of the subject. But maybe you dare to give an answer. How far are we actually away from a complete digital twin? Do you dare to predict, or do you dare to give an answer?
Yes. Well, there's a lot of talk about so-called data doubles, how we as individuals are actually almost like followed by a shadow or a cloud of our own data, which is then called this data double. To be honest, and I think it's very, very apparent in these Corona times where we're basically all grounded at home, we still yearn for physical meetings. There's this beautiful term, skin hunger. We want to embrace and touch and rub against each other, so to say, which I also said in the talk, is part of what life in the city is about, to be near one another physically. Yeah. So I think we will never fully either get there, and if we would, we wouldn't accept it. So I'm quite sure that the physical contact, even in the smart city, will be paramount and key. And I'm quite sure that we will see more of a hybrid form rather than a displacement of physical contact.
Okay. There is a new question coming in, so thank you, audience, for popping up the questions. Do smart cities benefit from the social cohesion?
It's a great question. I think my argument would be that I would kind of inverse this question by stating that a truly smart city is a socially cohesive one, because together with collectives, you can achieve much more than individually. And yeah, I think a city that is actually open and equitable and fair for everyone to live in is a city in which there's less social disparity and where technologies serve to benefit the lives of the large majority rather than just singling out certain groups as privileged groups. So yes, I'm a very big fan of this notion of social cohesion as part of thinking about smart city alternatives.
Okay, Michiel, thank you very much. In view of time, we have to stop over here. I would like to ask you, please stay online, because in the end, I would like to have you face for 1 minute back on the stage. Thank you for now, and see you in 20 minutes. This brings me to the last speaker of today, which is Professor Angèle Reines. She's a full professor at the University of Eindhoven. And in addition to that, she's an associate professor at the University of Twente and a visitor professor in Sydney. She will talk about how to achieve 100% solar energy supply. Angèle, the floor is yours. Good morning. Yeah. Please go ahead.
Thank you. I go to the clicker and try to see my presentation. And could you check whether you can see my presentation there? Yes, wonderful. So there's a slight delay, I noticed. Sorry for that, but I'll try to manage this. Okay. Good morning, everybody. In this presentation, I would like to explore whether it's feasible to use this sustainable, inexhaustible energy source, the sun, for all our energy demand. So that's actually what I aim at, 100% solar energy supply for mankind. And in this presentation, I will show how this might be done and whether this is technically and also societally feasible. We know the sun as an enormous source of energy with a surface temperature of close to 6,000 Kelvin and a very high power emission. And to give you an indication how small we are with regards to the size of the sun, I show this picture. And as you notice, Earth is very small. And to enlarge the size of these pictures, I included a close-up of the sun and Earth. And it's very interesting because of the distance in practice. We have at the sun a surface luminosity of about 64 10 to the 6 watts per square meter. And all that energy is emitted to Earth and results in an enormous amount of yearly energy of close to 4,000 zettajoule. And this is very interesting because we use actually on an annual basis 600 exajoule as mankind as a whole for heat and electricity, which means that in practice we receive on Earth about 6,500 times more energy from the sun than we consume. So just recalculating that in time, every 1.5 hour we receive from the sun our annual energy demand, meaning that we only would need 0.1% of our earthly surface in a sunbelt country to generate power from the sun. And that looks like this. Actually, this is a technical approach of the question, how can we achieve 100% solar energy? So I would say from a physics perspective, we can just answer this question very simply by, yes, we can. We can achieve 100% solar energy. But it's also necessary because as we all know, we have to face the problem of climate change in the next decades. And as you can see in the left graph, solar energy supply results in a CO2 emission reduction of factor 20 as compared to fossil fuels, together with the other renewables, meaning that it's really significant to try to achieve the highest possible solar energy share in our energy consumption. But this is not new. We went through several energy transitions already in the past. And at the moment, we are somewhere in a phase where we have to transition from close to 90% fossil fuel consumption to modern renewables, presumably with 100%. But we already went through this transition from the Middle Ages to the Industrial Revolution. And I have to apologize for this time scale, because in the past, the time is longer than in the future. So if you look back in the past, the time scale goes over centuries. Well, in the future, we have to look at 30 years. So it is a really interesting challenge, because how can we actually move from a society that was mainly based on human power and the use of biomass, mainly actually solar energy driven resources, to a new society that's also based on these sources. And that's actually a really big societal challenge, meaning that if you want to use solar energy, which automatically implies that we use wind energy, biomass, and hydropower, that we have to look at our energy flows in the world. And this is a very nice graph that I took from Stanford University that shows the exergy flows on a daily basis. And here you can see that the solar inflow to our planet, to our terrestrial system, outrageously outnumbers our fossil fuel consumption, which is actually also mainly solar energy, but captured in carbon that was produced in the past, made from biomass and plants that grew in the sun. But in practice, we hardly use this enormous solar energy source. That's a pity. And though we have a huge amount of solar radiance given by this map, and many countries that have actually a great solar potential, we still have to consider how to better embed all this energy in our actual energy system. But as mentioned before, we only need a very little bit of our surface, particularly in a sunbelt country, to be able to produce all this solar power. And usually this happens then in deserts, where every day, the whole year through, we have an extremely high solar radiance of in the order of 6 kilowatt hours per square meter per day. An example is shown here in Dubai, where they work on the largest concentrating solar power plant called Noor Energy in the desert. And this looks a little bit like a futuristic picture, but this is the reality. This is actually already being installed. And it makes me think, what if we produce solar power in the desert? How can we actually produce it to countries where we need energy outside these deserts? I think this is going to pose some kind of challenges to international collaboration. But anyway, technically seen, this is possible. The big problem actually that we have with solar energy is that it is an intermittent energy source. And this moving graph shows the solar spectrum over a day. And you notice it's moving a lot. But the changes can be dealt with in the flexibility of our electricity systems, for instance. But we can't deal easily with the day to night variations. And we also can't deal with strong seasonal variations of the availability of solar irradiance in climates at higher latitudes. This means that our maybe dream image, but I have to say it's not my dream image, to install everywhere solar panels and cover large surfaces for the production of solar electricity, might not work for large-scale implementation. Therefore, we have to look again at how different energy needs from our society can be covered by different forms of solar energy. So actually we need electricity, thermal energy, and fuels. And there's different technologies that can offer those different forms of energy demand. For electricity, we know photovoltaic conversions. For thermal energy, we have the use of thermal conversion in fluids and materials. And for fuels, we can actually fall back to photoelectrolysis and chemical processes. Now, this is really interesting because we can apply these forms of solar power in different uses for infrastructural applications in buildings and in transport. And I have to say, for the fuels, it's really interesting to directly feed them into infrastructures, either gas infrastructures or transportation infrastructures, and actually in that way supply indirectly electricity and thermal energy required for instance buildings and transport. But the problems with storage still remain. So for the different levels of energy demand, the storage problem becomes larger. So for thermal energy, we only have a seasonal problem, but for electricity, also a day to night problem. So a short-term problem, and also even a short time scale problem at the minute scale with large scale implementation. And I think also in that context, solar fuels can help to solve these issues. Though I have to say that some of these fuels are still in development. So the TRL levels are not high enough yet for large scale implementation, but the potential is there. So resuming my introduction to solar energy in a societal context, we have to also consider that at the moment we have a centralized energy system. And of course, we can convert this centralized energy system to a solar-based system, but then we have to decentralize. So we have to think about distributed energy production and distributed energy consumption. So our whole energy system has to be changed in the future. And this is also a societal challenge. In this context, I think design and engineering approaches can help. So knowing that renewable energy is really a matter of relevance for the mitigation of climate change, and also to ensure that future generations won't be harmed by our present energy consumption, we can consider design, which is actually designing a society in a new way, such that it meets the human needs with regards the use of certain technologies. And actually, in that way, we can support this renewable energy transition and maybe find other solutions than if you only would create new technological solutions. This means that we have to look at solar energy problems in an interdisciplinary context. So not only improving technologies, not only reducing cost, but also looking at the societal aspects like regulation and law and how we can adapt them to make the situation more favorable for solar energy technologies. And I think also very important is to include human factors. And these are the acceptance of the public, but also the perception of people and the interaction of people with new technologies in their situation of living and use, like the topic of cities addressed by Michiel also connects to this. How can we create cities in which citizens can live together with solar energy technologies? And then also the topic of design and styling emerges, because as you look at something, you also like it to be looking good. Some examples of what you can achieve nowadays already with solar energy technologies is, for instance, you can create designs that fit to landscapes. You can create designs that have a coverage that can be adapted to any visual appearance by, for instance, pictures or graphic design as shown at the left bottom. But you also can integrate solar energy in curved surfaces and create different designs of buildings as shown at the right side. And also you can, for instance, integrate solar energy in windows. And this is a design I made myself for solar powered windows with patterns. And at the moment we see a really strong development of solar applications in electric vehicles, like for instance, Lightyear, Transsolar and IM Efficiency, 3 Dutch companies are trying to achieve, and so far with great success. This all works, but what if societal acceptance is not high enough? Maybe then we have to look into space. And it's really interesting to notice that, for instance, ESA, the European Space Agency, is promoting this sort of new forms of solar energy production. And then actually we have to think about solar arrays that will be launched and produce electricity that can be beamed back to Earth, meaning that you always use the highest solar radiant available in space without cloud coverage, of course. And also NASA is working on this sort of solutions. Here the challenges are not that much whether the design fits in the environment, but whether the design is lightweight and high efficient and doesn't need much maintenance. So summarizing, yes, I think yes, this is the last slide, thank you. I think it's really well possible from a physics perspective to use all energy radiated from the sun to Earth to achieve 100% solar energy supply to our mankind. I think it's really possible, but we need an energy transition to reach this physics aim. And that means actually that though we have a lot of Sunbelt countries with big deserts, with large area that can produce solar power, that might be an interesting solution, but also will pose international challenges towards collaboration and energy transport to places where a lot of energy is used. And also, if we want to better integrate solar energy in our society, then we have to consider redesign of buildings, infrastructures, and transportation means in order to bring along great public support base, which is important for these sort of technologies. And as I mentioned, if all this won't work, we always can go to space and produce solar power there, but maybe it might be a bit costly. So having said this, I hope that you can understand there's a lot of opportunities, and to my belief, the future will be really sunny. Thank you for your attention.
Thank you, Angel, for this very sunny and interesting talk. We have some time left for a few questions, so if you allow me, and maybe let's start with this one regarding the previous talk of Michiel, who talked about smart cities. How about integrating the energy transition with these smart cities? Can you elaborate on that?
This is a question to me?
Yes, please.
Yeah, I think there is a great opportunity because the city is of course the place where we consume most of our electricity, because the city, most of people live, also a lot of industry is based there, a lot of economic activity, and also a lot of transport. So if the energy transition will take place, it will be predominantly allocated in a city and actually built environment, to my opinion. And that also means that if you want to manage these energy systems in a proper way, then you might need to use smart applications with data processing and data analytics. Yeah. So it's going to be a smart system also in the end.
Yeah, exactly. Well, maybe related to that, Angel, would transport, it's a little bit more generic question, but it's also related to the previous one, would transport of solar energy harvest from a sunny side to a rainy country or whatsoever, would it be possible with the current infrastructure, or do we really need to improve or change the infrastructure to allow this?
Not that much, because actually I'm involved in IEA task on PV for transport, and we discussed two possible directions. We also wrote a report about it recently. One direction is vehicle integrated photovoltaics, for instance, and then you can actually integrate solar energy in electric vehicles. And depending on the size of the battery in the EV, you actually can achieve a very high yield for, let's say, solar coverage of your energy need for transportation. So you have to think about the solar drive range in the order of 4,000 to 10,000 kilometers per year, depending on the climate, where you apply this sort of new products. On the other hand, you also can think about solar charging stations that are integrated in infrastructures like grids. Then, of course, you have to change something, but the solar power station can be added to a grid and also can be used separately. So it can be installed separately as an autonomous power station. So I think it's not going to be, let's say, a big challenge to apply solar energy to transport.
Okay, then maybe as a last question for today. This all seems to work really well, but why hasn't it been integrated yet? What do you feel is still required to integrate the stuff?
Yeah, of course, it's a very good question. And this is, I think an innovation question, because we already have an established energy system that functions well with all the based on fossil fuels. And that means that all our supply chains and all the logistics and everything is based on this sort of energy carriers, which worked fine for a while, but of course it results in high CO2 emission. And the climate change issue is at the moment the biggest driver behind renewable energy transitions. Mm-hmm. But I have to say, there will be changes, because solar power can be produced now below the spot price of the electricity grid in Europe. So solar power is cheaper than coal-fired plants power. Okay. Meaning that actually the financial hurdle we always heard about, the financial barrier, is not there anymore. So I think it's going to happen in the next decades.
Well, with this sunny answer, I would like to close this session. Thank you very much, Angel. I would like to invite the speakers again to the floor. So this was the session I concluded over here. I hope you enjoyed it all very much. I'd like to thank all the speakers once again, the speakers over here, the speakers at home that made it able to do this. I thank Peter and all the crew over here for enabling this session. I do hope that we can be back next year with a new NNV session at the Physics Veldhoven 2022, and hopefully live at the Koningshof in Veldhoven again. Thank you for now, stay healthy and see you then. Bye bye.